ChatGPT can be very cagey about how it answers questions. Yeah. For example, just who am I? Yeah. Does it know who Stuart Cording is? Yeah. Well, a year ago, it said it didn't know who I was, but when I pressed it and said, oh, he's an author for a lector, all of a sudden his memories jogged and, oh yeah, I know who Stuart Cording is. He does this, that, and the other. However, ChatGPT assigned me as the author of a couple of books which I've never written, because I've never written a book. Let's move on 12 months, same question, and apparently ChatGPT's never heard of me. Yeah. Despite saying, this that guy that works for a lector. It's like, no idea. And of course, in a year, I've actually produced more content with my name on it, not less. So how I've suddenly become a missing element in his memory, findable. Not entirely sure.
So, hello and welcome to Coffee and Tech, the podcast powered by coffee and our passion for electronics. Today with us we have Stuart Cording. Stuart, welcome to our podcast. Together with Stuart, we have with us some cappuccino and some espresso macchiato. And Stuart, to quote your LinkedIn profile, you are deep tech journalist, electronics influencer. You collaborate regularly with Electro Magazine. Thanks for being here, first off. And I wanted to ask you if you can do a little introduction about yourself, through to share some of your journey in electronics. What's been the changes you've seen and your own development in electronics, in the semiconductor industry? What inspired you to go into the field of electronics?
I think the inspiration came very early in my life. My dad was an electrical engineer, and so there was always that element in the household of him working on building sites. He used to take me with him, and I'd see all this equipment installed in new buildings in London, all over the place. So we used to spend time at the British Library, for example. It was a huge project near St Pancras Station. There's also the so-called Big Bang, which is when the stock exchange in the UK moved from paper-based trading to computer-based trading. And so I sort of followed him around all these places, and I had this feeling for what engineering was. I understood what sort of electricity was and all these things. And, other things as well, like having electronic sets to build circuits and things like that. So that was integrated very early on. I'm a 70s born child, so I grew up during the 1980s, which was also that period of microcomputers in the home. We bought a Commodore 64, and that was the central point for programming, learning how to program, understanding what a computer could do. We used to get books from the library, for example, and learn about how you could interface with the computer. We'd sort of connect to light sensors and temperature sensors, measure how quickly a cup of tea cools down, things like that. A traditional British problem. And so that was really interesting to have that combination of electronics. Here I can build something to control something, make a radio, control lights, sense things. But then with the computer, then you learn how to sort of program those things. So it was inevitable, really, that was going to end up in electronics. There's also a natural interest in Lego as well, which I think a lot of engineers share, that ability to build something. There's that Lego technology as well. So you've got lots of gears, so you could build things that moved and pneumatic systems, things like that. So that was a natural interest. Going through school, at the time I did what was called craft designing technology, or CDT, and again alongside manufacturing and mechanical elements and woodworking and welding and things like that, there was also the opportunity to learn about logic gates and amplifiers and those sort of things. So a lot of the projects I did at school were heavily electronics focused, which then of course eventually led me to go to university and study. But before I actually got to that point of studying, I sort of had a bit of a crisis when I left school at 18. I'd done my A-levels, hadn't gone particularly well, wasn't really happy and didn't really understand what to do next. So I managed to find myself a job at an electronics manufacturer called CMAC. Now, their focus at that particular site was quite interesting, sort of from the history. They'd come out of what was called STC, or Standard Telephone and Cables. It's a company that had been sort of focused on the telecoms industry. And the telecoms industry had obviously moved on from relays and copper wiring, was moving more towards digital technology. And they had a whole range of technology, mostly focused on oscillators and crystal filters and things like that. But it was like an ecosystem in there. They manufactured everything. So we had autoclaves where quartz crystals were grown. They were then sliced and diced and prepared in their cases. And then we had manufacturing teams manufacturing them, testing them, all the quality elements. And we also had a research and development team, which is where I ended up at, after a few years there. That gave me an opportunity to see the whole sort of manufacturing process from concept right through to manufacturing, and also the quality elements that go through that. And that's really sort of sat with me throughout my entire career as a knowledge base, as it were, for how things happen. And I don't think, looking at today's manufacturing, those ground principles have changed much. I mean, so I think there's quite a lot there that I can still draw upon, and I do draw upon today in communicating about our industry. And they let me go to college one day a week as well, which was really good. So I was able to sort of build up those qualifications that you needed, and eventually went to university and decided then, makes sense. I can see that the value a degree has for my career.
That's a very, very, very interesting story, and I think probably many engineers find themselves also in a similar situation, right? Some type of curiosity as kids, Lego. That's a passion I share, as well as when you are confronted with this decision of what do I want to make of my life, thinking, well, I don't know, right? Like, I know I like tinkering with things, but you might not know how good the match is from a certain study to what you really like to do or what your skills are.
Yeah.
So I think it's very, very interesting and rather common in many engineers. So you have a very extensive experience in the field of electronics, and so according to your experience, how has the field of electronics development, all the way we develop, the solutions we use, changed over the years?
I think it's changed beyond recognition, essentially. Yeah. So if we look back to the 1990s, so I started working for CMAC in 1994. We had computers in the office. Yeah, we had Intel-based PC and the IBM PC architecture as a PC. We had, but in that situation, also networking. Yeah, but it was like a 1 megahertz network between all the devices. It was a coax network, so you took about one pulled apart cable, and everybody's access to the network then went down. And that network was only on site. Yeah, we didn't have access to anywhere else. So, for example, we had an email client, but we could only email each other in the office. There was no,
of course,
communicating with people outside. Another aspect was all the data sheets would come, with all those thick data books, and everybody loved to have the data books there. You'd have sales engineers coming from the semiconductor vendors, for example, to share the latest updates. And that was a really big thing. Everybody in the office was, on Thursday, so-and-so's coming. And that was going to be the time when you were going to get the updates, the information, maybe new data books, which replaced the old ones. So this ability to quickly grasp some data or compare things wasn't there like we have it today. It was really paper-based. Even desks we had, they were designed to sit there and work with paper, and just putting a computer on a desk took up the whole space.
Really?
So when we look at your offices here, for example, a completely different layout. So the expectations were massively different. I think that access to information was limited, but also access to tools. Yeah, so back then we had a PCB design tool, an EDA tool, and it was expensive for everybody. When they had a certain number of licenses, some people had a dongle to be able to use it. And then compared to today, you can go online and actually use a complete EDA tool online for free. So there's a marked difference there. And I think also at that time when I was studying and I needed to do my own projects and things for college and then later for university, it was great to be in that environment because you had access to those tools which you couldn't have at home because you couldn't afford it, and also you had access to amazing digital and analog test equipment of a quality that again you could not have at home at that time. So
Absolutely.
you had when you went to borrow a piece of lab test equipment, it was on a trolley. You pushed it around the office. And today, you've got a little box that plugs in via USB or Ethernet or even wireless. So those are some of those big changes. So I think those are the sort of areas where you look around and go, well, that's changed a lot. I think some of the difference, some of the things that have stayed the same is the basic principles. So we were designing oscillators mostly. And if you wanted to design a new oscillator, you didn't just like pull out a blank sheet of paper and start drawing stuff. You took a previous design and modified it for the new specifications. But then there were other sort of research areas. I think one of them was on oven-controlled oscillators. That's something the team had never done before. So that was basically starting from first principles for aspects of the design. The oscillator was understood, but not necessarily the heating to control the temperature of the oven oscillator. And another area was we were working on an ASIC at the time, which basically took everything that was in a quartz crystal oscillator and put it on a single piece of silicon. And again, that was a big research project as there was no basis for that. And I think today, when you look at engineering companies that I visit, I've been an FAE, a field application engineer for many years, traveled all over Europe and parts of North America. And when you see how they develop things, again, you take a standard design and modify it for a next generation or an improvement, or if it's research and development, you really have to sit down and do some really detailed engineering to get going and start with something new.
Yes, actually, that's something that we get a lot. One of the, I would say, biggest, not the biggest, but one of the biggest hurdles when you are developing some electronics is you need to whether base your work on some existing piece of work, right, which is almost good practice. It saves you a lot of time.
Yeah.
Or if you don't have, if you're not that lucky, and then you need to start from scratch. There's no other way around sitting, reading data sheets, and maybe asking around in forums, checking magazines. You need to source some information to get you started, because we discussed also something like this in the former session of the podcast. The thing is, you begin with a set of requirements as an engineer, but that's not the end product, right? The deliverable in the end the last deliverable is the board. The precursor to that is going to be the EDA project. That's where you will start working. That's your realm as an electronic engineer. But you need to, before you reach your kingdom, your realm, you need to walk a certain path of going from requirements to finding which components do I need to fulfill the requirements, to find then all the bells and whistles around them to make them work in the way that you intend, and then capture everything in the EDA tool. On top of that, today you need to be mindful, very mindful of supply chain, right? It's not like you can pick any passive or any component. Chances are you're going to find that at least 20-30% of your BOM is not available anymore, right? So there's so many things that you have to take into account. And regarding actually this point, I want to ask you, based on your experience, what are the most significant challenges that an electronic engineer faces right now when it comes to developing some electronics?
It's interesting that you pose that question. I think the challenge we're facing at the moment in the industry as a whole is obviously a lack of what we call STEM or STEAM students. The science, technology, engineering, maths students coming into the industry. That's the first challenge. And what worries me the most is that we spend a lot of time out there talking to people, and I go to lots of startup events and things like that, And what we often see is a startup coming along and they're building something on a platform that already exists. So especially in the world of software as a service, somebody's come up with some sort of AI tool, for example, like ChatGPT is obviously a popular one at the minute,
Yes.
or Midjourney for creating images. And everybody's building on top of these platforms. And it's nice. There's loads of great innovation going on in there. But my worry is who's then working on the next Midjourney? Who's working on the next ChatGPT? And inside our industry, who's then looking at maybe improving power converter design based on SiC and GaN to really push efficiency into above the 99% range, and working on getting high density designs with multiple watts per cubic inch, because I think those are challenges as well, and they're innovations. But I don't see anybody sort of doing that hands-on hardware development and as much in the details. It seems to be, let's take something that's already existing and build our value add on top of that. And that worries me a little bit. The other worry is that obviously there's all these young engineers coming into engineering environments, and they are, generation sort of millennials, Gen Y. We've also got Gen Z on the way. I'm sort of a little bit concerned about how they are going to acquire the knowledge that I acquired when I went into industry. Sort of the current generation of engineers, Gen X, and also boomers. Boomers are retiring. Gen X is very, very busy. So you're wondering how much time do they have to look after their teams and pass on that what we call tacit knowledge. Yeah. So all these engineering organizations, they know why there's an RC circuit on the base of a MOSFET, for example, or why these particular ferrite beads are used. There's loads of stuff like that there are no hard and fast rules for. It's just years of experience. There's this joke where they invite a retired engineer to come and look at a machine, and he comes and looks at the machine, which nobody's been able to repair, and he just gets out a piece of chalk and he puts a big cross on one part of it. He says that's where the problem is. So the current employees go in, open it up, and sure enough, that's where the problem is. And he sends in a bill. They say, send us the bill, doesn't matter what it costs. So he sends a bill for like 10,000 euros. And they say, oh, it's a bit much. Can you break it down for us? And he writes, well, it's €1 for the chalk cross and 9,999 for knowing where to put it. And that sort of summarizes, I think, in a lot of ways, that tacit knowledge that needs to be shared. Experienced engineers, especially in the mechanical domain, for example, they just stand there in a factory and listen to the noise of a machine. Go, yeah, the bearing's going on that, and sure enough, take it apart and the bearing's going. So this sort of information sharing, making sure that you're robust, so that when people retire or leave, that the knowledge is still there to make sure the next generation of engineers can take on. So I think those are the sort of the key areas where I think we need to do better and need to take a look at those things.
Yeah, that's a very good point. There are things that there is no way around the experience, right? There is no way around having heard many times these machines, so that you can tag these 9,999 to know where to put the cross.
Yeah.
And I've spoken with many engineers, and nowadays, because I think each time has its own challenges, and they can adapt, right, as time changes. Some things become easier, some things are harder. In the past, you had huge booklets or books with all the data sheets from a family of components, of certain type of components. The market for components was smaller, and now you have. It's easier to find the component that you need. It could be easier because you have way more offer, but also because of that, you find yourself in a sea of options. And if you don't have that experience of years, you might not be able to solve it as quickly. Or even if you have that experience of years, you don't know what's the last thing on the market, right? And you have to go from an idea of a request to creating your PCB project, and I am not even touching any EMC testing, any manufacturing, design for manufacturing. I'm not touching those things, because that then it becomes it's a miracle. I always say the same. It's a miracle to create a PCB. It's a miracle. That's why I think every engineer, when you think of the PCBs that you have created, they're like your babies. You cannot help but being a bit proud, right? They are your little miracles. Here at CELUS, and I'm using this as a segue for the next topic. We have, when you think about development, you can think of different layers of abstraction. You have the idea with the basic high-level concepts that you need for your board. That's the highest level of abstraction. And then you have the lowest level of abstraction, which is the components and the connections, right? Which components do you need? If you had to read all the data sheets, by the time you're done, there are probably double the amount of data sheets available now that you've read, that you still need to read. Half those data sheets are now obsolete. So there's no human way of really making the best decision. Using your brain. And what we here at CELUS do is we have to speed up this process and automate this process. We have an intermediate layer, which is how do you automatically go then from the highest level of abstraction to the lowest level of components and connections, and that's what we call the Kubo. Mm-hmm. Kubo, probably my Italian, Greek, Portuguese colleagues or the audience will say that I am wrong, but I will claim here, because they cannot tell me anything, that Kubo comes from Spanish. And it means bucket, and it means cube. So, and the same way a bucket and a cube works, a bucket is a vessel where you can put things, right? And a cube is a multidimensional object. So a Kubo is a multidimensional bucket digital datasheet, because I can put in this container all the information that I have in a datasheet, so that in the end you end up with something that is better than a datasheet, because you have everything digitally codified. You have application, you have the specifications, you have the EDA files, you have optimization factors, as it could be efficiency, size, price, and you have supply chain information to make sure that every time you consume this data, you have it up to date, and you're not going to find yourself having some passives being obsolete. And this is the core, right? These digital datasheet that we call Kubo, that connects, allow then a machine, our solution or software, to go from the highest level to the lowest level automatically. And I'm telling all these because behind these, there is AI, right? It's very important if you have to digitize data sheets to turn into Kubos. On our solution, there are different aspects where AI is present. And actually, they mentioned it at the beginning. My fault. But today we are going to explore the role of AI in electronics development. Which brings me to ask you, because I know that you have some experience in AI yourself, right? You've written a 3-piece article about neural networks. I've read that you've developed your own Arduino library for neural networks. So I want to ask you, what are your learnings from this experience?
Yeah. Well, I think one of the most important things to understand is it's not new technology. I mean, AI has obviously been brought up to the higher level of mass understanding through the media, through ChatGPT, through Midjourney tools that allow us to do some amazing things. But the reality is the kernel thought of making a machine that can learn and can sort of operate like the human brain has actually been around since the 1940s. So there were some engineers and scientists out there. One of them is the McCulloch-Pitts network, for example, which was developed in the 1940s. And the idea there was this principal process of looking at the brain and saying, right, the brain's obviously got these signals coming in from nerves. And it's not thinking as such, but it's using past experience to make a decision based upon some sort of weighting. Yeah. So this signal is very, very strong. This signal is very, very weak. This one's very strong, and this one's somewhere in the middle. And that combination of nerve endings which delivered that, maybe from touching something that was hot, plus a memory and all these sort of things, that led to the idea of, well, I couldn't make a decision out of that. How could I train a single neuron? And so that we could then build a machine that was built out of many neurons and capable of learning things and remembering things in some way or other. I think one of the that worked well. It's sort of called a weighted sum calculation, and you sort of put numbers into the neurons to sort of weight how the output was going to respond. Some further work that was done on that was by Frank Rosenblatt. He developed something called a perceptron, which was like an early forerunner to the neuron, electronic neurons we've got. And he sort of worked with more variable thresholds in his decision-making process. But the challenge that they found at that point was it was very easy to, for example, replicate functions that were linearly, or challenges that were linearly separable. So, for example, if we look at an AND gate, that's very, very straightforward. If we've got two ones, there's a one at the output, otherwise it's a zero. And so we've got a very clear line. If I draw that Carnal map for it, I just put a line through the middle, and it's either zero or it's one. Same with same with OR or NAND or NOR and all these other types of gates. But where it was falling down was with XOR, exclusive OR. So the problem we've got there is that two zeros make a one and two ones make a one. But if we've got 1 and 0 or 0 and 1, it's a zero.
It's a zero.
Yeah, so it's not linear separable. What we have to do is it doesn't matter how I draw my map, I've always got to put a circle around the two numbers, the ones or the zeros. And so these early neurons weren't capable of doing that. So what came next was this idea of how can we modify the decision-making process, and there had to be this sort of like differentiation element to it. So what came out of this was something called the delta rule approach, which led to the use of what's called a sigmoid function. And the way you can sort of visualize that, if you imagine that you have an x-axis and a y-axis. Now on the x-axis, what you have is a line that goes up like a little hill in the middle. And there's the same area under the graph either side. So if we say 0.5 is where the hill is, and then towards 1 and towards 0, it sort of drops off. Now, if you drop a ball directly onto the top of the hill, that ball will quickly go either to the right or to the left, but it can't stay there in the middle. You sort of force it to move in a direction. And this was sort of like a breakthrough in that it allowed us to sort of make these neurons move quickly to some sort of decision and not get stuck somewhere in the middle. And there's a guy called Matt Mazur, who I found online. He'd written a long paper about sort of a bit about the background on how it works and also the mathematics behind it. And based upon that, I then wrote my Arduino library that copied it. And again, it goes back to this point I made earlier, is that my worry is that we spend too much time using stuff like mobile phones, like 5G, like Wi-Fi, without the real understanding for it. And through the article and also the development of the library, the idea was to sort of go out and say, look, this is what's behind all of this and how it works, because we also still need to be able to understand how neural networks form a complete AI model of some kind, and how we're going to train it and teach it.
That's fantastic. It really sounds like taken out of a Blade Runner piece. So I've also read that you have some experience when talking about AI in non-cloud applications. So I want to ask you, what does it mean, AI in non-cloud-based applications?
Well, I think when we look at all of the different AI applications that are out there, ChatGPT, Midjourney, and so on and so forth, these rely on cloud-based computing. So these are the big data centers run by companies like Microsoft with Azure and AWS from Amazon and Google. And they have enormous amounts of computing power available. And it's not just processor power we're talking about hundreds of GPUs alongside a processor to do all that difficult multiply and accumulate type calculation, which is important for these types of the maths behind AI. And of course, if you have that as your background, it's almost like being the CEO of a company. You can make amazing things happen. compared to a small company, but that's only because you've got a team of 20 or 30 people behind you actually executing the things you want to do. And then we've got other applications which are what we call at the edge in the industry. That means that's where the data is being collected, where the sensors are. And we do need, on occasion, some sensing and analysis of the data at that point. And AI offers a huge amount of potential in many, many applications. So, for example, one company I've talked to in the past is Eurotech. Probably not that well known, but as a high performance computing company. But essentially, what they do is take a high performance computer and put it in a very small box, about sort of this size, by comparison to a server in a data center, and you can actually put that into a vehicle. So they have water cooled processors in there as well. The whole system's water cooled, and they use the automotive industry uses those computers for inferencing. So when you look at the training process for AI, we start off maybe with cloud-based computing to help us train a model. Can I recognize pedestrians? Can I recognize cyclists in that automotive domain? Can I recognize traffic light colors and things like that? But at some point, we need to sort of compress the model down to a manageable amount that's possible in a computer that can be integrated into a vehicle. We don't, especially with the challenge now is the move to electric vehicles. I don't have endless amounts of energy all the time, with a motor running with fossil fuels. Now I have a battery with a limited capacity. So firstly, can I get it down to that level? And then secondly, although I've trained my data, I also need to go and sort of check it out and see if the model I've created works on the road. So what they do is they do an inferencing process. So they take the model they've trained, they connect the PC to all these cameras, all the sensors that are in a car. So we're actually trialing everything on the real system under real conditions, but it's not driving the car. All we're doing is seeing if the model we've created under real conditions is capable of seeing all the things we'd expect. And then you compare the data that was recorded from all the sensors, especially the video cameras, for example, and see if all of those aspects of the road experience are being detected by the model as you'd expect. And is it responding correctly? So that's a really huge, powerful edge type application. On the other hand, there's also lots of applications where we could benefit from AI because the data we're analyzing is very, very difficult to decode using a standard procedural programming process. So one of the examples that I was using for my little Arduino AI project was to detect the color of traffic lights, for example. Now, in order to detect, we've got a camera, okay, we've got RGB colors, red, green, and blue, but I'm trying to detect the difference between a red light and an amber light and then a sort of green light. Now, I know approximately what I would expect. Obviously, if I'm looking at a green light, I'd expect the camera sensor to see lots of green, but the amount of green is going to be dependent on other factors, the exposure of the camera, how much light is coming in, is it day or is it night? You might have a value of 255 for the green pixel, but it also might be 128. And you don't know what the red and the blue are going to be by comparison. There's also an element of blue in green too. So you'd expect low red, but maybe a bit of blue. And it's different in different countries. In the US, you used to have sort of like blue-colored go lights, and we have more green-colored go lights. So there's this three-dimensional aspect, obviously RGB for sensing colors. It's very difficult to write a switch statement or a series of if statements. They get very convoluted in order to detect all that out. And then you've got other aspects like exposure, you've got brightness, is it a really bright green to everything else, or is it a dull green? So many factors, you come in a fourth dimension. So that's something where AI is really strong. Another example is measuring the ECG signals from a heart. Again, it depends on the sensor, it depends on the human. We know from medical scientists what the shape of that signal should be. But it's, again, procedurally in software, very difficult to say what the differential should be to detect a rising edge here, a falling edge here, and all the other aspects of that. And these are things that AI do really well. But I can't connect everybody who's got a heart problem to the cloud. I can't rely on the internet being there. More bandwidth requires more power. Lower bandwidth is less, but will I get enough data through? Will I get a response back in time? If someone's got a heart problem, you need to flag that up quite quickly. It can't be sort of, oh, we've analysed it an hour later. I can now tell you that you're not feeling very well.
It might be too late.
Exactly. So this AI at the edge is really important. And I was talking to Ambic Micro, for example. They do a lot of AI-based stuff as well. And they're very much concentrating on being able to do AI in a very low-power microcontroller. So there are so many aspects where I think AI can play a role. Probably more machine learning, if you want a proper term for it. And we need to be able to explore those things, but it requires a good understanding of what AI can do and what it can't do, and how it's implemented. I think that the key thing about AI for me is it's really pattern matching. You teach it the pattern that you want to detect, and it's very good at recognizing complex patterns in many dimensions. But the challenge remains, how do you get the data? How do you train it? How sure can you be that the data that you've sort of trained it with erroneous data, so as it doesn't mix up signals and information? There's a really good example which I was covered in one of my magazine articles, where scientists were sort of training AIs to detect, let's say, ships, or horses. And in the case of the ships, it was really good at detecting ships. But when they actually analysed the model, what they found out is it wasn't detecting ships at all. What they built was an AI model that was excellent at detecting sea. And it had actually gone, well, the ships are relevant. Every time I see sea, there's a ship. So that's the thing. And then also you show a picture of a fish jumping out of water, and it goes, oh, there's a ship. Or the other one was they trained it on some data where there was of horses. And on all of the pictures, they also had like things that weren't horses. The problem was all the pictures with horses, many of them had some sort of like watermark of the auctioneer that was selling the horse, or the person who's the owner of the horse. And so basically trained itself, if there's a watermark, then it must be a horse.
Yes.
Yeah. And so this is the thing to understand. Okay, so is the data clean? Am I giving enough good examples? Do I have enough non-examples or wrong examples to say, yeah, you might see this, but this is definitely not what we want. So, and my concern is maybe if we don't have a good understanding of the entire process, the ecosystem, how to tackle the training process, we're going to sort of miss out some good opportunities, and not be able to implement things the way they should be.
Yeah, I actually heard of one of these examples, an AI trained to try in a medical environment to try to identify breast cancer before any human could do. And it turned out what the AI actually was identifying was this ruler that is put on the edge of the picture. And then, well, if there was a ruler, that because it came from a real picture where a patient had been taking the image, and then of course there was breast cancer. It was almost there. I always keep in mind that there's a very nice picture of a how's it called, a hallucination from AI. The prompt must have been something like, please draw a salmon going swimming up the river, and this picture generated a very nice river with a very strong flow, but the salmon was a piece of salmon from the supermarket, so a very orange looking square. So that's why it is so important to understand, right, what they're doing, how it works, and what do you use it for. Nowadays, I think when we speak AI for the general public, everyone thinks LLMs, everyone thinks ChatGPT, Midjourney, DALL-E, you name it. But it's this type of, and it's important. There are many flavors, and you can use it in many different ways. For us at CELUS, we use it in different areas. One is to generate these cubos, to generate these digital data sheets where you get the application and everything for the components. We work with manufacturers because for us, quality is very important. If you are getting into one of these troubles, AI-powered issues where you end up connecting things wrong or having the wrong values in a certain schematic, that is going to cost time, money, and loss. The engineer is going to lose the trust on the tool, right? So for us, the CELUS Design Platform is the place to go to give you the best advice. As a human being, as we established, you cannot read all the data sheets, right? So essentially, what you do on the platform is you capture your requirements as a very high level in the shape of a block diagram. And we have the AI in different aspects. I said content creation because it's important if you are going to capture the technical requirements of your project and you want an EDA project out of it generated automatically, as it is the case. You need solutions, right? You have your questions, you place your questions, you have created your very complex search query, but you need solutions. These solutions are the kubos, and we need this support to generate them in collaboration with manufacturers. But then it's also important, one, how the translation of the requirements is done. And here, for us, it's important to use, it's very useful to have AI in different aspects of the platform, but it is very important for us that the engineer is still is the one behind the steering wheel. Is still the one making the decision. So the platform is going to offer you, is going to discriminate very quickly thanks to the piece of AI that we have implemented in the search query procedure, and it's going to give you a certain set of candidates for your circuit, and then you as a human can decide, because all those are compatible with what you want, which means that then you can not only get to your prototype in hours or minutes instead of months, because you're going to shorten all the research phase a lot, but you can also adapt. If you have any problem, you get new requirements, right? It won't be the first time that a customer says, you know what, I am going to change your requirements midway in your project. So you have a lot of flexibility there, and AI is key, not to substitute, but to really boost and give the engineer an ability that is not yet available to the common of the mortals, right? And taking into account the different types of AIs and your experience in electronics, how do you perceive the role of AI in transforming the industry of electronic design, right? Particularly in electronic design tools?
Yeah. Well, I think the first thing to say is that we still need to be very careful with what tools like ChatGPT actually offer us. So I work for Elector, for example, as a trade magazine or electronics magazine. And one of my colleagues, Brian, actually used ChatGPT and some of the other tools, AI-based tools out there to tackle a project. So he wanted to basically create an egg timer from the Tower of Hanoi process. So you're moving these rings backwards and forwards. And that was going to be his sort of a mechanical egg timer, as it were. Now, his experience was like ChatGPT provided some very good approaches, was very clear about what was needed and everything like that. But I think one of the things that came out of that was he'd already said, look, I'm an electronics engineer. I'm very good at software. I'm very good at electronics. My challenge is with the mechanical side. But despite that, ChatGPT kept sort of coming back and saying, oh, I can help you with the software. I can help you with this. I can help you with that. He said, look, that's not, I know that bit. I don't want help with that bit. It's part of the solution. I need to concentrate on this part. And then he tried to use sort of like the visualization element of the tool as well to create some diagrams to help with the mechanical design. And it was absolutely hopeless. I mean, it's just drawing boxes and circles and lines. And he's, it knows it needs actuators, it knows it needs servos, it knows it needs motor control and the algorithms to do that, or at least the software to do that, but was, hopeless at then turning that into a visual element. Yeah. So I think there's big bits there. One of the other things I see, I spend a lot of time interviewing engineers and then creating articles and white papers and ebooks on various topics to sort of collate knowledge. Yeah. So, and I do that because it's really important that we share this information amongst our community. The challenge I see with all of these AI tools is what is the source data that these things are being taught on? Now, if we look at, we don't really know. I think that's the first challenge. And if we look at the internet as a whole, let's assume that these large language models are being trained on publicly available information. The electronics industry must be a sub decimal point percentage of everything that's out there. Some of the information's good, some of it's bad. We know that as engineers because we already use Google to search for information. So what information is it drawing upon? And also ChatGPT can be very cagey about how it answers questions. Yeah. So I've been doing some research over the years. Now, for example, just who am I? Yeah. Does it know who Stuart Cording is? Yeah. Well, a year ago, it said it didn't know who I was. But when I pressed it and said, oh, he's an author for Elector, all of a sudden his memory is jogged. And, oh, yeah, I know who Stuart Cording is. He does this, that, and the other. However, ChatGPT assigned me as the author of a couple of books, which I've never written because I've never written a book. Let's move on 12 months, same question. And apparently ChatGPT's never heard of me. Yeah. Despite saying, this guy that works for Elector, it's like, no idea. And of course, in a year, I've actually produced more content with my name on it, not less. So how I've suddenly become a missing element in his memory, not entirely sure. But then when we come into sort of real technical questions, there's this S11 parameter for RF systems. I am not an RF expert, but I was required to write something about it. Now, the idea is this S11 parameter sort of measures how much of a signal is transmitted and how much is reflected back. And that's quite important in antenna design or, for example, microwave heating. We want as much as the energy to go into what I'm heating and obviously nothing to be pushed back into the amplifier. But again, no clue. Is absolutely convinced that sort of 0 dB is the point of good transfer of energy. But then looking at a website such as antennatheory.com, they've got exactly the opposite, saying 0 is where it's all reflected. There's that you don't want that, and you're going like, so you questioning, and it comes basically back with the answer. So you need to be as close to 0 dB as possible, but then says 0 dB is actually not what you want to be in the same answer. So the worrying thing is that you sort of rely on these answers and even go back and question and query them, and it still doesn't seem to know what it's talking about. There's also another example where you can confuse ChatGPT. There's an issue with silicon carbide MOSFETs, for example. And if you regularly pull the base much lower than is allowed on there's a negative limit to the base. Over time, you can disrupt the structure of the device, which causes its properties to deteriorate long term. So then I went back and asked about, what would happen if I was to, what are the negative impacts of operating a bipolar transistor within the specification of that's given for the base? And it comes back with this long ream of potential problems. But essentially what I've asked is it okay if I operate a transistor properly? And the answer to that is, yes, it is okay. So, and again, it's sort of like making up all these excuses as to why it could be bad and all these sort of things. So this is my worry, is that if you don't have enough engineering expertise and background and you start to rely on ChatGPT, it can be a bit worrying. And also the fact that in all of its answers, and maybe this is a reflection of sort of the marketing impact on a lot of commentary. When we look at, let's assume it's learned from websites on electronics, trade magazine articles and things like that. Some of those are written by engineers, some of them are not, some of them are more marketing focused. And I don't know maybe what it's like with other domains, but what we see is it can be this. I mean, there's an indirect relationship, and you go, okay, so it can be, but under what conditions? If it's an indirect relationship, what's the direct one? Yeah, or when you say indirect, you mean it's indirect, or you're just holding back from making a commitment to my question? So I think these are big concerns. In actually just relying on ChatGPT alone, a large language model. So we've got to be very careful, I think, as how far we rely on these tools and the models that are out there.
I agree. That's indeed. You need to be. You don't know how much is lack of knowledge, how much might be some implemented lack of specificity, very strategic lack of specificity, not to get in trouble. So you, and I think that's why I really like the approach that we're taking here at CELUS is not, you need to have the knowledge, and we're boosting what the electronic engineer can do, rather than saying, you know what, you can go home, you will do this in 30 minutes, and we will solve it all for you. I think, sure, over time, probably, I don't know, in 10 years, maybe with the speed of development in 5 years, you can get close to that, but never to that point. And actually, I wouldn't like it personally, right? Because it would mean half of us wouldn't have a job. And I tend to like to pay my bills. So, yeah. So, this topic is huge. And I want to ask you, if you had a how's it called, a crystal ball, what would you see in the future of electronics development and AI?
I
What do you envision?
Yeah, I think we need a nuanced approach. Now, I think there's obviously a huge capability there. As we've started with the conversation, we've got young engineers coming in. We've got tenured engineers, unfortunately, leaving the industry. How do we do that knowledge transfer? How do we allow engineering organizations to retain that knowledge somehow? We also need to fade out some knowledge. Yeah, I guess if we started developing, applications based on valves, just because that knowledge was there, that's going to be a bit of a problem. And we also need to sort of factor in the hype tools and the hype technologies against the industry improved ones. Yeah, so microcontrollers, for example, we've moved from 8 to 16 to 32-bit. Everyone uses 32-bit today, but then someone comes along with the transputer or something like that, and there's a lot of hype behind that. But then the reality is it's transpired to nothing really. It's not really a technology we're using. So that needs to be sort of factored in. And can does it make sense for AI tools to even consider those things, or do we just push them under the table straight away and be more controlled? How often do we need to train these tools? So we might come up with we might be using a particular model. We need to train it with our data. How often do we need to retrain it? Do we keep the old knowledge or do we scrap it? It's like when I was quite surprised actually how much innovation goes on in magnetism, for example. You think magnetism is a phenomenon which is well understood. I don't really recall much coming out of magnetism since maybe the 19th century or something. But people are still innovating that space today and doing new things. But what sort of technologies do we see then saying, well, that's fully understood. We're all agreed that that's the state of play today. And it won't need touching for 10 years, but something else might need touching every year or two in order to keep your AI basis of knowledge for the organization up to date. I mean, the biggest challenge for me is I think the first place is that these tools, whatever they are, and I think ChatGPT has sort of really missed an opportunity, is to provide the sources for where it's found certain types of information. And I was at a startup event recently where there's an AI tool on offer. I think it's ChatGPT based, it's a back end that they've built on it. And you can feed it with all the information you have within your organization, and then you can sort of ask questions ChatGPT style. And then that tool actually comes back to you with an answer, but along with that answer is a series of documents. And so you can actually go in and say, okay, what did that document actually say, and use your own understanding to decide, was that a good source or a bad source? Because again, you don't know how clean the data is that's going in. There's the other thing as well is, what do you rely on if you've got semiconductor vendors, for example, which is my area of expertise. I know how data sheets occur. I know how application notes come to life. Sometimes it's just somebody with an idea, literally an idea they've been working on, and someone says, oh, it'd be good if we sort of wrote that down and everything. Doesn't mean that's state of the art or the approach to use it. But of course, they're going to write about it in a method that says this works and everything else, but it doesn't necessarily mean that you can actually turn it into a product. So that's an issue. And one of the other areas, I was actually talking to your team to sort of understand a bit about how AI is being integrated and what's being looked at. I mean, the initial problem is actually getting to that source data. And one of the biggest challenges is obviously data sheets are very varied. If you turn a data sheet into a text document, for example, the formatting, the text is all over the place because it's all done in columns. You never know quite how they're going to come out. The images can be variable. What information is in the image? Does it really relate back to the text properly? A lot of a lot of data sheets and other documents, they're actually repeated. So I've got version 1 of this product. Version 2 just uses the same images as the previous one, and if there's a mistake in it, that mistake carries on. Now, the mistake, that's not confirmation of accuracy. It's just that nobody's seen it.
Exactly.
So that's part of it. And tables apparently are a very difficult thing to understand for these language models. The other thing is about intellectual property, for example. Now, when I started in the industry, I always thought getting a patent, for example, would be a really big, important thing. I thought, it'd be really cool if I could get a patent at some point. But then I started looking at some of the patents that colleagues of mine had acquired. And it's literally just 2 parallel transistors making some constant current output for a HD converter or a temperature sensor and things like that. And you look at it and you go, is that really patentable? Yeah, I mean, I've seen that before. It doesn't look innovative and novel to me, but yet these seemingly standard circuits and sub-circuits can be patented.
Yes.
We're already seeing huge amounts of fighting between large players, in the industry, arguing over who has the patent on particular processes in RF, for example, and how basebands are built and all these sort of things. So what happens then if you've in good faith taken the response from this tool, which has been trained on application notes and reference designs and all these things, and yet you end up in a patent situation because you've used a circuit which you thought was just available. And even the reference designs as well. I mean, I know reference designs are made. I mean, maybe it's improved, so some companies are better than others, but just because you've got a reference design doesn't mean you're going to get it through an EMC test.
Yes.
Yeah.
Exactly.
Doesn't mean you're going to pass safety standards with it. So in how far can I, even without AI support, trust the information that's out there, even from established manufacturers? So I think those are really big things. I think one of the things we need to look at, in parallel to training these models, is that firstly, quoting the sources has to be a big thing. And I use Grammarly a lot because I write a lot of content for people, and I want to make sure I'm not plagiarizing anybody. So I think we also need to consider some sort of plagiarism tool in these design tools that says, hey, you're using this particular circuit element, or this block of processing, be aware that there's these patents out there.
Yes.
So it's it's difficult to say at the minute which way it's going to go, and how competitive companies are. So and who looks at what, even if you're manufacturing hundreds of something for an industrial automation platform, probably no one's going to notice. But you're selling smartphones, and there's millions of those getting out every year, and your chipset copies someone else's IP, then someone is going to take interest and look at that.
You're going to get into trouble.
Yeah, indeed. Exactly. So.
Yeah. Actually, I think quality is very important, and it's in some aspects when one talks about AI, is always completely overseen. You just take whatever the AI gives you. That's why we at CELUS put so much emphasis on surfacing information, telling where it comes from and letting the user decide. Which brings me to the question: where do you see? Because you've talked to colleagues, you also in the past with Tobias Paul, with our CEO. So my question is, where do you see CELUS fitting in all this environment?
Well, what really attracted me to the CELUS environment from the very beginning, which is a few years ago I first discovered it, and initially I think, like most engineers, I was a bit apprehensive. It's like, oh, hang on a minute, you're suggesting circuit blocks to me. I think it's my responsibility as an engineer to do all of that, and I don't want somebody else telling me what to do, how to do it, and all these things. So I was a bit apprehensive initially, and I think that's the general. Engineers always push back when anything new comes along that takes away their autonomy in making decisions and developing something. But the more I looked at it, the more it made sense, and it comes back to that early period of my career when I was working in a research and development team, I said, well, actually, it's how we've always done it. If I need an RF circuit and I need an amplifier or an oscillator, whatever it is, I'm not going to start again from first principles. I'm going to use what I already know and adapt it and modify it, and make sure I can still fulfill the specifications through that. So, with that respect, and having played a little bit, I'm not power user by any means, but having played with it a little bit, it's very sensible to sort of say, yeah, I need a temperature sensing element in my circuit. It needs to be analog and connect to an A to D converter of a microcontroller, or it needs to be digital, and I prefer to use I2C for power reasons and things like that. So I think all of that is very clever, and I think that's really where we need to go, because we need to be more efficient. We need to get to our result faster. And I think by merging the tool as it stood a couple of years ago to the AI elements you're adding in today is definitely the way forward. I think that's the most intelligent way forward. And I think as long as that's managed correctly, as we've said, by making sure we're clear about the sources of the information, that we know what the limits are and how much can I trust this, we can do a lot more. And I think we can help the community as a whole be more rapid in their progression from idea to a product. And I think that's essential, because what we see on the market today is that electronics can have a massive impact on people's lives. I think the biggest area where we're going to see growth and impact on lives is in healthcare, sort of wearable medical. And I also think the other area we need huge progress is in energy, turning green energy solutions, turning solar into electricity, and the other bits and pieces that come along with that, and also being more efficient with power, converting power for motors, for example, with motor inverters more efficiently. We desperately need to move those areas forward faster, and take the benefits that new technologies like SiC and GaN offer us, and the new topologies that we can use in order to create less heat generation during the conversion, and also come up with lighter, smaller solutions, as vertical takeoff aircraft that are electric as well, things like that. So for me, the quicker we can share knowledge and information, as far as it's not secret source, company secrets,
yes, of course,
the better. And if CELUS and the environment you provide can be part of that, it's a really strong, powerful platform, I think, for the future of engineering in electronics and embedded systems.
I do agree. So last but not least, to wrap this conversation up a little bit, I wanted to ask you for audience. So essentially, a piece of advice based on your experience, also on your expertise regarding AI. What would be your advice for future generations of electronic engineers that might be watching us or listening to us? Makers, people that are passionate, teenagers that like to tinker with Lego techniques. What would be your advice?
I think the most important thing is to keep at it, is to keep trying things. Don't give up when something goes wrong. And also, as far as possible, network with people. I think as engineers, we tend to be a little bit held back. I mean, I probably break the mold a bit as a more expressive person, ready to approach people and talk. But it's not the normal sort of expectation of an engineering person. We tend to be a bit held back and a bit quiet in group environments and things like that. I think it's really important. When I was a kid, sort of like 13, 14, I used to go and do placements, so I worked at the BBC for a week in the Easter holidays, for example. I used to, as I said before, I used to go with my dad to building sites and just see how engineering happens, how these electrical systems are built in. And I think that's really what you need to do. Is if you really find it exciting and interesting, go out there and learn as much as possible, talk to people, find out about what they're doing. And I think we as an engineering community need to do more. I mean, I really appreciate the efforts that people make in regards of STEM, for example, at colleges, universities. We need to do more of that. We need to and that's sort of part of my personal mission for the rest of my career, and why I'm so eager to come along today, was that I want to be somebody that people can turn to and say, hey, tell us more about that. What is it really? I think the mainstream media glosses over lots of things, and this is bad, that is good. It's very black and white. Engineering is always a trade-off. It's 80% of this and 20% of that, and that provides the best we can do today. And we need to prepare that in 5 or 10 years' time, that might be the wrong method, or not the most optimal method. So I think stick with it. Learn a programming language. Whether it's on a PC or an embedded system, Arduino and Raspberry Pi have made a huge difference, as well as the BBC Microbit, for example. Really push stuff out there. I think for young kids, Scratch is really good as a programming environment. And other than that, it's just do what you enjoy, and probably also take a look at Rust as a programming language. I think there's a big future there too. So.
Yes. So right before we finish, Stuart, thanks a lot for being here. If our audience wants to follow your work, where could they find you?
The easiest thing is to put my name into the internet. So in Google, I come up quite quickly. LinkedIn is obviously a good place for a business environment. I'm on X as Stuart Cording. I do some stuff on Instagram as well, as I think Stuart.Cording. So I'm easily found there, and also search on the Elector website for articles I've written as well.
Wonderful. Thanks a lot. And to the audience, thanks for being there. Thanks for listening or watching our podcast, and we'll see you in the next session. Bye-bye.